Hi, welcome to Matter and Energy Part 4. My name is Dr. English, and in this tutorial we're going to be talking about specific heat capacity and heat transfer. Specifically, we're going to be talking about the law of conservation of energy, what is heat, specific heat capacity, calculations with specific heat capacity, and finally heat transfer. So let's talk first about the law of conservation of energy. Just like the law of conservation of mass and the law of conservation of charge, we have the law of conservation of energy when we look at matter and energy. And basically, the law of conservation of energy states in any process, energy is neither created nor destroyed. In other words, we need to keep track of all the energy within the system in which we're working. So the amount of energy that is released also has to be the amount of energy that is absorbed, and we need to account for that. This can be applied to situations where energy is transferred from one object to another. An example of this might be like hitting a baseball. We have a transfer of energy from the bat to the ball, or pouring hot coffee into a cold ceramic cup. The energy in the coffee is going into the cup. Energy is also transferred from one kind of energy to another. So for example, igniting a match, it's going to transform chemical energy into heat energy and light energy. What is heat? Heat is defined as energy that flows between two samples of matter due to a difference in temperature. One where it's hot, another where it's cold, and watching that transfer of energy. When we measure energy changes, we use the joule, which is represented as a capital J, for the unit for energy, work, and quantity of heat. And we find that on table D of your reference table, right down here. There's that capital J. Another table that I just want to point out that we're going to be using later on in this tutorial is table B, where we will be identifying specific heat capacity of water as a liquid as 4.18 joules per gram Kelvin, or degrees Celsius. Pretty interchangeable. So I just wanted you to be aware that those two tables do exist and they're there to help you. Now let's talk about specific heat capacity. Energy added to a substance in the form of heat is used to break small positive-negative attractions between different molecules and/or ions, causing an increase in random motion. In other words, an increase in kinetic energy of the particles that make up that substance. The amount of heat needed to increase the temperature of a substance 1 degree is about the same regardless of how hot the substance is, but the amount varies from substance to substance. So whether I have water at 10 degrees Celsius or 20 degrees Celsius or 100 degrees Celsius, the amount of energy that's needed to raise it, no matter where the temperature is, 1 degree is still approximately the same, no matter at what temperature I start. Because different substances heat up in different ways, we need some way to determine how much heat energy is required to raise the temperature of a given substance. This is where we look at the specific heat capacity of some common substances. The specific heat capacity, or C, of a substance is the quantity of heat needed to raise the temperature of a unit quantity of substance by 1 degree. So if I look at any of these substances, to raise the temperature of these substances, no matter what temperature they start at, 1 degree Celsius, I need this amount of heat. So for example, water as a liquid is going to require 4.18 joules, that's our measurement of heat, per 1 gram in 1 degree Celsius. Aluminum, on the other hand, only requires 0.89 joules. So what you're going to see here in this particular table is that water in its 3 different phases of liquid, solid, and steam have very high specific heat capacities compared to these other substances down here, where if we look at our list, we have aluminum, iron, mercury, carbon, silver, gold. The majority of them are metals, with the exception of carbon, but the majority of them are metals, and they are going to have much lower heat capacities compared to our molecular substance of water. So now what we're going to do is we're going to look at some calculations involving specific heat capacity. So we're going to use reference table T, and our formula for heat is Q equals mc delta T. We're going to be using this quite a bit, where Q is our heat in joules, C is in our specific heat capacity, and we are going to see this labeled as either joules per gram degrees Celsius, or we'll see it labeled as joules per gram Kelvin. Because we know raising a substance 1 degree Celsius is the same as raising it 1 Kelvin, these are pretty interchangeable. It just depends on what temperature scale you're starting with. M is mass and T is change in temperature. And when we are given change in temperature, in other words, in terms of a temperature initial and a temperature final, in order to find this delta T, we're going to use the idea of taking temperature final minus temperature initial. So we're going to have to pay attention to that, because that's going to ultimately tell us how much energy is either absorbed from the reaction or how much energy is released from this reaction. So let's look at our problem here. What is the total number of joules, so we're looking for joules, of heat energy absorbed by 15 grams of water when it's heated from 303 K to 313 K? Okay, the first thing I'm going to do is write my formula. Q equals mc delta T. And when I do this, my mass is 15 grams. My specific heat capacity is 4.18 joules per gram Kelvin. I'm looking at my temperature change here. I'm going from 303, which is my temperature initial, to 313, which is my temperature final. So I'm going to do temperature final minus temperature initial. So my final temperature is 313. My initial temperature is 303. So the difference here, my delta T, is 10 Kelvin. So I'm going to put 10 Kelvin in here. And when I multiply this all together, I get 627 joules. And joules is what I ultimately want to be in. So how does my units cancel? Well, grams is going to cancel grams on the bottom. Kelvin is going to cancel Kelvin on the bottom, and I'm left with joules here. So I know all my units have basically canceled out, and I'm left with what I want, which is my heat, which is 627 joules of energy absorbed, because this is a positive value. If it's a positive value, so we should make a note of that. This is a positive value. So therefore, therefore, energy absorbed. A 10-gram sample of water cools from an initial temperature of 288 K to 280 K. Calculate the amount of energy lost, so we're going to have energy released, by the sample during this cooling. So we're going to have Q equals mc delta T. So again, I'm looking for the amount of energy, so I'm solving for Q. My mass is 10 grams. I am dealing with water, so that's going to be 4.18 joules per gram, and we're still in Kelvin. And then my delta T. So my temperature final is 280. My temperature initial is 288. So when I subtract those two, I'm going to get a -8. And all this negative means energy released. So energy is going to be released rather than absorbed. So don't worry about the negative. The negative is fine. So we're going to have -8 here, K, and I know 0K is absolute zero. I understand that, but ultimately when we look at our Q, the Q is going to be negative, which just means that energy is released. So if I multiply together 10 times 4.18 times 8, I'm going to get -334 joules. So that's, again, that just means energy released. So the amount of energy released by the system, as we see here where it says energy lost by the sample during the cooling. So this is our final answer here. Let's look at our last example. 3,780 joules of energy is absorbed when the temperature of a water sample changes from 293 Kelvin to 323 Kelvin. Calculate the mass of the sample of water. So instead of solving for Q this time, we're solving for mass. So the first thing that I'm going to do is write my formula. Q equals mc delta T. So they give me a number in joules. So 3,780 joules. I'm solving for mass. I'm still dealing with water. So I'm going to have 4.18 joules per gram Kelvin. And then again, I look at my temperature difference. So we're going to do temperature final minus temperature initial. My final temperature here is 323, and I'm going to subtract that from 293, and when I do that, I'm going to have a delta T of 30 Kelvin, and it's a positive number, which means the energy is absorbed. So over here, I'm going to have 30 Kelvin. So if I multiply and divide out and I solve for mass, ultimately my mass will be 30.14 grams. And if I look at all my numbers, I need to go to 3 significant figures. So my final answer, to be more accurate, should be 30.1 grams. 30.1 grams. Now let's talk about heat transfer. Since temperature is explained in terms of the motion of molecules, the fact that heat flows from hot items to cold items must also be explained in terms of the motion of molecules. So here we have a box representing a hot sample and a box representing a cold sample. When placed in contact with a cold object, a hot object warms the cold one. So if we see here comes my hot object, it's coming in contact with my cold object, and we could see over here that the molecules are basically going to be moving over into the cold area and transferring the energy. The reverse does not occur. The cold doesn't cool off the hot. When molecules collide, the faster one with more kinetic energy will transfer some of its energy to the slower one. This results in a transfer of heat energy and a change in temperature. Another way of looking at it is this figure right here. So we have box A and box B. Again, box A is representing hot and box B is representing cold, and then ultimately we're going to mix them together. So in this figure, the gases come in contact. These two boxes would come together. They exchange energy until they reach an equilibrium. In other words, reach a new average kinetic energy. Energy is transferred from the molecules originally in container A to those in container B, hot to cold. We say that the heat energy flows from container A to container B. So what did we learn in this tutorial? We talked briefly about the law of conservation of energy. We looked at the concept of what is heat. We talked about specific heat capacity. We did 3 calculations with calculating specific heat capacity. And then finally, we talked a little bit about heat transfer. Need more help? Feel free to contact me. Have a great day.